Hey, welcome, and let's take a look at 11.1, which is our introduction to properties of parallelograms. That's kind of a fun word to say, parallelograms, but we'll take a look at a few things. I have a little Desmos activity that I'm going to show you a little teeny bit to motivate what's going on. This is mainly for people that were gone for the lesson, and I know there are some because of the sports that are out there or illnesses. I've got a few people that are in that situation. So anyway, without any further ado, let's take a look at our little set of notes. What we're going to do is we're going to, again, talk about the properties of parallelograms. A PDF version of these notes is sitting online right now. Let's see if I can make this get straight. This is all crooked. Let me see if I can make this look straight. That looks a little bit better. Okay, so let's start off with what the properties of a parallelogram happen to be. I'm going to move my little icon up here to the top. So before we do that, let's talk about what a parallelogram is. And a parallelogram is a quadrilateral. Now, the first thing that we have to do is break that part down. A quadrilateral is a polygon with precisely 4 sides, which could be a rectangle. Quadrilateral could be a rectangle, it could be a trapezoid, it could be a rhombus. There's a lot of them, but a quadrilateral, a 4-sided figure in which both pairs of opposite sides are in fact parallel. So an example of that would be something like this right here. And this is kind of a classic look of a parallelogram. Something like this, where these 2 sides right here and here are parallel, and these sides right here and here are parallel. It's a really nice, simple view of a parallelogram. Of course, it's perfectly fine to sometimes have a parallelogram like this. And I'm using the grid that is provided on this set of notes because it just makes it nice. Now, a lot of you guys might think of this as a rectangle, and that is true, but what I can also tell you is these are definitely parallel, as are those. So when we look at a parallelogram, some of those parallelograms could be rectangles, some could be squares, but regardless, it's a figure with 4 sides where the opposite sides are the same. But before we get too far into that, we want to also establish another little fact, because we have learned a few things and about triangles in the past. And what we're going to try to do is we're going to try to utilize facts that we've already learned about triangles to expand into our understanding of quadrilaterals. So we're just going to make a couple of quick quadrilaterals. I got one right there. Here comes another one right here. I'm kind of making it just whatever I felt like making it. Here's one right there. I was hoping it didn't look too much like the first one, but it could. I'm going to go ahead and make one that looks almost like a trapezoid here. I'm not going to be too careful to make sure that it's perfect, but we've got just a couple of quadrilaterals, nothing particularly special. But if we go into this thing and we just draw a diagonal between any 2 non-adjacent vertices, the ones that are across from each other, it doesn't matter which 2. Just jump across. And what you're going to notice is that every single time we take a quadrilateral and we draw one of the diagonals in, we don't want to do both, you don't need to. What you're going to find out is that we have formed 2 triangles. And so what we already know is that if I were to take a look at this top triangle right here, this angle, and this angle would add up to 180 degrees. But I could also judge that a little bit further and say that this angle, and this angle also independently add up to 180. So if that's true, the 3 pink angles plus the 3 blue angles would have to be equal to 360. So we have a nice little saying that the sum of those angles is 360 degrees. I'm going to just write that right here. So just like we knew that every single time you add up all the triangles to get 180, we know that we can always add up the angles of a quadrilateral and get 360. And again, if we go over to this one, we could see that the 3 blue angles would add up to 180. The 3, I'll go again with some kind of a pinkish color, the 3 pink ones. But if you look at those, all of these angles, that's blue and pink together, that's blue and pink together, all of those angles would have to add up to 360 degrees. Give me 1 second and I'm going to let's see, let's do this. Nope, I don't want to do that. Let me go ahead and stop that share, and I'm going to go ahead and. Okay, so let's look at a very, very simple little example of that I generated here, where I have a quadrilateral right here, quadrilateral VSTU or VUTS, depending on how you want to do it. And we know that somehow, because it's a quadrilateral, it must have a sum of 360 degrees. So if I could add all three of these values together, let's see, I could take 9x plus 2. I could add that to 20x plus 5, add that to 90 degrees, because notice I was being nice and I made a right angle there, and 13x plus 4. All of those angles grand total together would have to sum up to 360 degrees. Well, I want to go ahead and do a little combination of like terms, because I know I had 9x's here, and I had 20 more x's there, and I had an additional 13 right there. So I had a total of 42 x's, didn't I? But then numerically, there was a 2 here and a 5 here. So let's see, I got 2 here and 5 there. And 90 is a like term because it's a number, and I had 4. And all of those added up to 101, but I know we got 360 degrees grand total. Well, now we have a very, very simple algebraic story where I could subtract 101 from both sides. Let's see, 360 minus 101. We're looking at 259 is equal to 42x. I feel like I'm wondering if something is wrong with what I have, because I remember this answer being a little bit nicer. Did I make a mistake? I did. I blended two questions together. Let me fix that a little bit, everybody. Actually, never mind. I'm just going to let it go. I'm just going to let it go. We'll just stay with this. And we've got 259 divided by 42. 259 divided by 42. And I got 6.16. Okay, so we got 6.16. We got this kind of ugly number, but I didn't want that ugly number. I wanted to find the value of angle V. So I need to take that number X and multiply it by 9. So I'm just going to take this thing and I'm going to hit times 9. Now notice on my calculator it says A and S, and the last answer that I had was this 6.16 guy. So 6.16 times 9, if I add 2 to that, boom, I'm going to get 57.5 degrees. And that would be an application of the fact that we know that they add up to 360 degrees, so we can go forward. Okay, so let's go a little bit further forward. So when we look at a parallelogram, what makes it a parallelogram is that these opposite sides are in fact parallel. But what I wanted to do is give you a quick observation and help convince you of something. So I created a little, what's called Geometer's Sketchpad view over here. And in Geometer Sketchpad, what I did is I created two lines right here that are parallel. So notice if I draw this one up and down, I'm creating these various lines in this shape right here in the middle. No matter what I do with it, I can drag things around. I've got a couple of points. And no matter what I do, that region in the middle is going to be a parallelogram because I forced the problem just to make parallel lines. And I looked at how those sets of two parallel lines would connect, and I can move them in all sorts of ways, but I can't break the fact that they're parallel. But as such, I then went through the process and I hid some of those lines so you can't see it a little bit more. And I just looked at that piece in the middle and noticed that I can still move things around a little bit. But in addition to moving it around a little bit, I told the computer to start measuring a few things so we could kind of get a feel for different ideas. And so although I told the computer nothing but to make parallel lines and then measure whatever happens, all I told it is to make parallel lines and then measure them. What you're going to notice is not only are the sides A, B, and C, D parallel, you're going to see that they're exactly the same length. So these opposite sides are exactly the same length. So not only are they parallel, if they are parallel, they must be congruent. You'll also notice if you look really, really carefully, this angle B right here, angle ABC right here, and this angle ADC, see these have exactly the same vertices. they are also equal. So these opposite angles, these angles that are across from each other, are the same. And I can pull on this and create all sorts of differing shapes. You know, I can make it different, but no matter what I do, I cannot break the fact that these opposite sides are the same and the opposite angles are the same. And there's one other thing that is hidden. I asked it to find this bottom angle A plus B plus C plus D, and I hid that down here. And I said, hey, computer, go find the sum of those four angles. And it doesn't matter what I do if I make the figure smaller, bigger, move it around, pivot it, no matter what I do, all of these measures keep changing. But the one thing that never changes is that the sum is 360. And also equivalently, no matter what I do, the sides across from each other and the angles across from each other are also congruent. So with that in mind, let's finish up what we were doing. So the observation of the side lengths is that opposite sides are always congruent. That's a really, really nice fact. We could also say they're equal, meaning they have the same measure, but if they have the same measure, then they're also going to be congruent. And then the observation too is that these angles across from each other is that opposite angles are additionally congruent. But again, if they're congruent, they are also going to have equal measures as well, okay? So what happens when their vertices is dragged? Well, we just saw that. If we moved it around, no change happens. The above facts hold. I'm just going to say remain true. I cannot break those things. So are your observations from A and B always going to be true no matter how we make that parallelogram? Again, that answer is a yes. It has to be true no matter what. And we've kind of tried to demonstrate that. Now, I want to tighten that up a little bit, and you'll see that in a minute. So here's the first thing. Here's our first theorem. The sum of the angles in a quadrilateral is 360. We kind of developed that already. Check. The opposite sides of a parallelogram. If you have a parallelogram, then its opposite sides are congruent. Check. Again, if you need to pause the video to write that down, go for it. The opposite angles are also congruent. Check. Now, we've kind of established those things, but we haven't really proven why there's true. I just showed you some examples that it seems like it holds, but why does it hold? And we get to do our first little proof. So what we're going to do is we are going to start off with A, B, C, D is a parallelogram. And that, of course, is my given piece of data. Now, please understand that when you do a video, you can always pause it so you don't need to worry about if I'm going too fast. You can come back and take a look at it. Now, if we know that this is a parallelogram and we decide to draw in the diagonal, just like I did on that previous, the first page of the notes, we know that the definition of parallelogram says that the opposite sides are parallel. So I can add this to my picture saying that AB is parallel to DC and that AD is parallel to BC. Now, the cool thing is, and this is why I actually wanted to do this particular activity when I am, is as we prepare ourselves for final exams, we've got a few things that are happening that I wanted to remind you of. And the first of those is that we would know that angle 1 should be congruent to angle 3. And I think we have a little bit of a boo-boo. I think we probably did something in just a copying error. I'm looking for something to do some whiteout, but I can't find it. So I guess I'm just going to do this. I'm going to say that angle 1 is congruent to angle 3 right here. And that angle 2 is congruent to angle 4, which is right here. And that's true because of alternate interior angles of parallel lines are congruent. Now, that's a lot of writing, but we know that if the lines are parallel, then the alternate interiors are congruent. And we also know that if you share a side, you have this. Now, if you go through the process, and I broke this apart so we could see it, I have this angle here, and this angle here, and this one. On the other triangle, I'm just separating them so we could see them a little bit better. I had this angle marked, and this side marked. What you could see between those two triangles is that they are congruent by ASA congruence. And so what happens as a direct result of that is if you know triangles are congruent, then you know all of the pieces and parts are in fact congruent. And one of those things is, notice that angle A would be congruent to angle C, and that was because of CPCTC. Now, for the sake of being quick, I also would like to note that AD, the side length A to D, would be the same as the side length from C to B also, because of CPCTC. I feel like we might as well take advantage of that. But if you look at AD is the side that's across from BC in the original one. So again, those opposite sides are congruent. But we could also say that AB is going to be congruent to CD. So all of these pieces and parts are going to be congruent because as soon as you draw in that diagonal, it forces two triangles to be congruent. Hopefully that was helpful. In another video, we'll put some quick examples of utilizing those facts and do one other proof. Hopefully that was helpful. I will see you back in class. And if you're gone for a tournament or something, good luck with the tournament. And if you are out sick, hope you feel better soon.